In this video, we're gonna discuss about the composition of square wave before we venture into the last experiment, which is about analyzing the spectrum of a square wave. So also, in your last experiment, you're asked to answer a question on why DMM perform poorer when measuring square or triangular wave over sine wave. So you may get some hint from the content of this video here. All right. So in short, right, you will learn all these information in another course very systematically. The course name is Signal and Systems, which is numbered as ECE 102 in the UCLA EE's course catalog. We'll not discuss too much about the mathematical details here. But we're gonna keep in mind the conclusion. One of the most important conclusions from that course is that any periodic signal can be decomposed into a sum of sinusoids at different frequencies. A square wave is also a well-defined periodic signal, so yes, it can be decomposed into a sum of special sine waves at the frequency of the, let's look at the equation here. So if we do a Fourier series decomposition on square waves with unit magnitude, what we get is that square wave is composed of a sine wave at the square wave's frequency plus a sine wave at 3 times the square wave's frequency plus a sine wave at 5 times the square wave's frequency with some diminishing constant coefficients, right, all the way to infinite frequency, right? So we can say that square waves are really made up of sine waves at odd harmonics, basically. For the word harmonic, what we mean is basically the first harmonic of any periodic waveform is the frequency of the original waveform, right? 1 over the period of the original waveform. The nth harmonic, however, means n is typically an integer, so it means integer multiplications of the original frequencies, right? So that means the third harmonic means 3 times the frequency. The fifth harmonic means 5 times the original frequency, right? So from theory, we know that square wave is really made up of odd harmonics, right? So let's see it pictorially. So the square wave we see on the oscilloscope we used to see is basically exclusively in time domain. What do we mean by time domain is that the x-axis here is always time. So this is a square wave we are familiar with. So this is its period, and 1 over that period is frequency. If we do some quote-unquote magic trick, this magic trick you will learn in E102 also is called Fourier transform. You will bring this signal into frequency domain. And as the name suggests, frequency domain, we have an x-axis whose unit is in hertz. X-axis is really frequency axis. So what we can, this picture with x-axis as frequency, y-axis as in dB scale. We'll talk about what it means by dB scale later. So this kind of plot, we call it the frequency spectrum of your original waveform. So I did a kind of like a sketch here. So this is more of an ideal case where you don't have any noise on your original square wave. So the spectrum should look something like this, right? So we can kind of, from a very high level, make sense out of this picture. We know that square wave is made up of odd harmonic sine waves. So let's see if that's true. So at the original frequency, you have some components here. You have some finite component at frequency of 1 over t. You have some component at frequency 3 over t, some components at frequency 5 over t, some components at frequency 7 over t. So it's really saying the same thing, right? Square wave is made up of sine waves at odd harmonics. If you add up all of these components together, you get back the original square wave in time domain, right? Don't worry about the mathematical details too much. So all you have to know is that square wave is made up of sine waves at odd harmonics, right? So let's talk a little bit more about dB scale and what it means. So dB scale, the first thing when we're tackling with an unknown concept is that we want to figure out its unit. So does dB scale have a unit? Actually, no. dB scale is always referring to a comparison, a ratio of something to a reference. So the exact equation in terms of power is this. So dB scale equals to 10 times log 10 of whatever power signal of interest divided by a reference power. Okay? And in terms of voltage signals, it equals to 20 times log base 10 of some test voltage that you're interested with over some reference voltage. Why 20 here? It's really because that power goes with voltage square as suggested in our last video. So by the rule of logarithmic operations, that you have when you have a square here, you can bring that square to a factor of 2 here. So you have an extra factor of 2 when you're talking about voltage comparisons, right? That means from this equation, you can immediately tell that if you have a dB number that's greater than 0, that necessarily means that whatever your interested voltage is, your test voltage is bigger than your reference voltage. Following similar logic, if it's smaller than 0, then Vtest is smaller than Vref. If dB is equal to 0, then Vtest is exactly equal to Vreference, right? So actually in our last experiment, we're gonna analyze the spectrum of a square wave by comparing the magnitude of each subsequent peak with the first peak at first harmonic in the spectrum, right? The way we're doing it is in dB scale, we subtract the value of each subsequent peak by the value of the first peak to get the experimental measurings that we fill in the chart. We fill in the chart after the experiment. So why are we able to do that? Remember, what we want is a comparison, right? It's a comparison between the nth peak with respect to the first peak, right? So what we want in dB scale is really 20 times log 10 of V peak at the nth peak compared to V at the first peak, right? We're able to do this very easily by just subtracting because of the rule of logarithmic operation is that whenever you do subtraction of logs, you're actually doing division, right? So in that way, if we want this quantity, we can just subtract whatever value in dB scale for the nth peak by whatever value in dB scale of the first peak. So that's pretty much about the theoretical background here. Let's move into the actual experiment.